For the first data type, let's begin with integers. An integer is a whole number. In an older system, integer appears almost everywhere. The card contains one burrito bowl, the restaurant has an internal ID, the customer has an account ID, a menu item has a product ID. The system counts orders, transactions, reviews, and available items. Integers work especially well for quantities that move in discrete steps. You can order one bowl or two bowls. The quantity naturally moves from one whole value to another whole value. Now look at this C statement. Int price lowline in lowline sense equals 1345 semicolon. Int tells it that this variable stores an integer values. Price in cents is a variable name. A descriptive variable name gives the reader business meaning. The assignment operator places 1345 into that variable. Here, 1345 represents $13.45 because the program stores the amount in cents. This technique matters because money requires exact accounting. Binary floating point representation approximates many decimal fractions. For example, a value such as 0.1 has a repeating representation in binary, in the same way that 1/3 becomes 0.3333, repeating in decimal. An application that handles order therefore benefits from an exact monetary representation. For a simple C application, integers cents provide a straightforward solution. A price of $13.45 becomes 1345 cents. A refund of 5.95 becomes 595 cents. Financial systems also use fixed point and decimal arithmetic models, especially when they support multiple currencies or sophisticated accounting requirements. The larger principle stays the same. The chosen representation prefers the required monetary precision. This is another useful distinction here. An ID may contain only digits while still having conceptual like a label. For example, order ID 8430192457 represent identity rather than quantity. Adding 5 to that order ID produces very little business meaning. This is why engineering requires both technical types and semantic meaning. Two fields can both use integers at machine level while serving completely different purpose in the product. The word integer describes a family of representations. C gives engineers several integer types because systems operate under different range and memory requirements. On many current platforms, an on-site char occupies 1 byte and represents values from 0 to 255. And it commonly occupies 4 bytes and provides a side range of roughly -2 billion through +2.1 billion. A long commonly provides a much larger range and works well for larger counters, timestamps, and similar values. The C standard defines minimum capabilities for these types, while the exact sizes depend on the implementation. This detail becomes important when software moves across platforms. Now consider why range matters. Imagine a counter that keeps growing. The current value fits comfortably inside the 32-bit side integer. Years later, the counter reaches the maximum representable value. At that point, the chosen type reaches the mathematical boundary. This is integer overflow. The lesson here goes beyond memorizing 2.1 billion. Every type creates a representable domain. Engineer requires us to estimate the future domain of the business data. A local restaurant may process thousands of orders. A national platform may process billions. A global event counter may grow even further. The business scale determines the technical range. Now we move to floating point numbers. A delivery platform continuously works with values such as distance, longitude, speed, estimated travel time, and the renting averages. Like, consider the driver's location on the map. These values represent coordinates around Chicago. A double generally provides substantially more precision than a float, which makes it useful when additional numeric detail matters. Floating point numbers are especially effective for measured quantities and scientific calculations because they domains frequently involve frictions and approximation. A driver's distance might be 1.2 miles now and 1.17 miles a few moments later. The value changes continuously as the char moves. So integers often model counting, while floating point values often model measurement. That distinction gives you a useful first institution when looking at the real software. Now let us move from numbers to human language. A food delivery application contains a large amount of text, like restaurant names, menu descriptions, addresses, delivery instructions, customer names. In C, one traditional way to store text uses arrays of char, like this part. So the important concept here is encoding. A computer automatically stores numbers. Characters therefore need a mapping between human symbols and numeric values. Axie provided an early standardized mapping from English letters, digits, punctuation, and control characters. Its original character set contains 128 values. Modern applications work with far more languages and symbols. Unicode provides a large universal character set, and UTF-8 provides one widely used encoding for Unicode text. UTF-8 uses a variable number of bytes for different characters. Common English XC characters occupy 1 byte each. Many other characters occupy multiple bytes. This becomes relevant when programmers allocate memory, calculate string length, cut text, validate database fields, or more text between systems. A string therefore looks simple on screen while carrying several layers underneath it. Characters, encoding, bytes, memory, and display. Now consider another category of information. Is the restaurant open? Has the customer paid? Is this menu item available? Has the driver accepted the delivery? This question describes logical states. C can express them through Boolean values, like this part. Boolean values make decision logic easier to understand. Modern CPUs commonly implement Boolean operations through integer-like instructions. The major engineering benefits comes from clear semantics. A field code is low-line paid immediately communicates its purpose to another programmer. That clarity becomes especially important as the code base grows. A small Boolean field can determine which branch of entire business workflow execute next. Boolean values work beautifully when a concept has two logical states. Some business concepts contain several possible states. Consider the order type. A DoorDash style system may support immediate delivery, pickups, scheduled delivery, or a group order. Representing these possibilities with an enumeration gives the program a finite vocabulary, like this part. At the machine level, these values can use integer representations. At the human level, delivery carries much more meaning than the raw number 0. This is a very important software engineering principle. Good code communicates business meaning to humans as well as instructions to machines. Imagine opening a large code base and reading this. Type equals to semicolon. The number requires extra context. Now imagine reading type equals to scheduled semicolon. The business meaning appears directly in the code. Enums therefore reduce cognitive load and improve maintainability. Now we can go one step further. An order consists of many related fields. The order ID alone represents only one property. The total price represents another property. Driver coordinates add more information. The address, payment status, and item all belong to the same conceptual object. C provides structure for grouping related fields, like this part. This structure models one menu item inside an order. Then we can build a larger order structure around it. This is the moment where individual data types start becoming a model of reality. Software engineering frequently follows this path. We identify properties in the real world. We choose suitable data representations. Then we combine those representations into larger structures. Later, structures can become arrays, linked collections, database records, API payloads, or objects in other programming languages. So the idea of a struct creates a bridge from basic data types toward data structures and the software architecture.